Magnitude of force. In this video, we'll be looking at the forces involved when we have moving charged particles in magnetic fields, as well as the motion of a charged particle in a magnetic field. So first we'll go through a few definitions. So current is the charge per time, meaning when we're looking at charged particles, typically we look at electrons that are moving in conductors through electricity. So the charge per time is how many electrons move past a certain point in a certain time. So the more electrons that move, the more current we have. The units for this are ampere. Often in my videos I just shorten it to amps. When looking at our right-hand rules that we've been using, we've been talking about conventional current. So back in the day, the scientists were considering that positive particles were the ones that moved, but now we know that the positive particles in the material are protons and they're locked in the atom and they don't move. In a conductor, the particles that move are electrons. However, the convention has still stood. So having a look at this diagram, electrons leave the negative terminal of the battery or the power source. Just picture an electron here. It would want to repel away from the negative terminal. So electron flow is this way. However, conventional current is just the opposite way. And it is the conventional current we use when we use our right-hand rules. So another definition is a current element. And what this is just a length of wire carrying a current. And the current element is its length times the current that it's carrying. The units for this are amps times meters. So we write it as AM. The magnitude of a magnetic field is the force per current element. So that's just our definition that we come up with. And from that we can create the equation below. This equation applies when the current element is at right angles to the field. The direction of the force is found by the right-hand palm rule. And in this case, if you want to test it, it's into the page. And the units are newtons per ampere meter. Alternatively, the units of Tesla are used often to describe this. The force on a moving charge in a magnetic field is given by I delta L times the magnetic field strength. Now, often we might have a situation where the wire or the current is not perpendicular to the field, however it is at another angle. So in this type of situation, we break the current element into its components with a vertical component and a horizontal component. In the diagram that you see on the screen, the angle that's created between the magnetic field line and the current element is this angle here. And the force is the same as it was before, however we add this sine theta term. And when it is 90 degrees perpendicular to the field, sine theta has the value of 1, which provides the maximum force. When the angle is 0, the current element is parallel to the field, which means no force. So that previous equation, we were looking at a current element when we've got moving charged particles moving through a wire. However, if the charged particle is not moving through a wire, it can still experience a force given by the equation on the screen. We still use the right-hand palm rule. However, what happens in this situation, as the force is applied on that particle, it shifts its velocity vector slightly. So observing the diagram, looking at the charged particle Q, it's a positive particle. If it's moving to the right, positive is a conventional current. So our thumb is pointing to the right and our fingers are pointing into the screen because the magnetic field says into the page here. So our palm is facing up, hence the force on the particle is in the up direction, perpendicular to the path of motion. As this force is up, the particle will move up slightly. However, as it is moving up, it is changing its direction. So when it reaches this location here in the field, we again apply our right-hand palm rule. Now our thumb is on an angle pointing in the direction of this velocity vector, which is the particle's path of motion. Our fingers are still into the page and our palm, however, is out in this direction. As the force is always perpendicular to the direction of motion, the particle is not getting faster or slower, it is just changing direction. And this results in a circular path. So in a previous topic we were looking at uniform circular motion, where the acceleration of a particle in uniform circular motion is given by the velocity squared divided by its radius. And looking at the force of this particle, using Newton's second law, we find that the force is the mass times velocity squared divided by the radius. Now, as we're looking at a particle in uniform circular motion here, we know previously that the force is given by this, but that's the same force of the uniform circular motion, which is the one we had just on that previous slide, and we can equate these two. We can simplify this equation to find the radius of motion is given by mass times velocity divided by the charge of the particle and the strength of the magnetic field. It's important when deriving an equation like this that we have a sentence describing why we can equate the equation, and we don't just use pure algebra to rearrange equations. The reasoning behind it is just as important as the maths. So looking at a scenario like this, the radius of the path of motion of this charged particle when it enters the magnetic field depends on the mass and its velocity, meaning if the mass of the particle is bigger or it's moving faster, the radius will be bigger. Also, as you can see, the radius of the particle is inversely proportional to the charge and magnetic field, meaning if the charge or the magnetic field is stronger, the radius will be smaller. We discussed a situation where the maximum force of a current element in a magnetic field is at 90 degrees and there's no force at 0 degrees. At what angle would the current element need to be in the field to be half the maximum force? So to assist, use this equation on the screen.